up here, up here, up here. Lot to do today. Still talking about air. So we were talking about Lagrange air. And so just as a reminder, so you should have had something like this written down in your notes. We usually think about it as just determining the error. We don't care which way we're off, which is why you'll often see like absolute value bars around these pieces. I think I had those probably when I wrote it the other day in your notes. The key thought here, remember that it's like we're trying to make a guarantee. So the whole thought is we're taking some function and we're going to try to approximate it, but on some interval, and I don't want to be wrong by more than whatever the guarantee then ends up being. So what we are looking at then is something like sine of x. So if I write down the first couple terms, again, this is one that you should probably know. So actually, I think we did sine last week. Let's do cosine. So cosine of x, if I wanted a Taylor polynomial of degree 4, take a second and write down those terms. So again, that notation might look like this, the Taylor polynomial. So the degree is what you have to pay attention to. Some of the terms may be 0. Through x to the 4th, not 4 terms. Because degree 4 would always actually be 5 terms, but some of them may be 0 in the case of sine and cosine. All right, so that should be enough time. So if you look at the screen, so I have the cosine function here. So your first term should have been 1. This was, an asked, but where are we centering it right now? At 0. We could have centered somewhere else. Remember, that's just a shift, right? We just substitute x minus 2 anywhere we wanted an x, and that would shift everything to the right 2. You could shift it to the right or left, whatever you want. So your second term should have been that. Remember, this is one that alternates, right? We get a plus minus pattern. The x term actually has a coefficient of 0. Why is that? Why is that x term missing? Sine of 0, because that's the derivative, and so it drops out. So this is the one where all the odds drop out. You notice n equals 3, the same thing should have happened. So this is what I was expecting you to write. And obviously you don't need to write that second one. The computer did that for some reason. All right, so if we think about this Lagrange error that we were talking about, we're talking about making a guarantee of we won't be wrong by more than whatever, and whatever we say there is our guarantee. So we'll do another problem here in a minute, but I'm just reviewing where we're at. So on Thursday, we were saying that most of the error, most of the issue is probably all wrapped up in what? That next term, right? So thinking of that, x in this case would be an x to the 5th term. Now that term here is actually going to matter. Don't think that that one's going to be 0, because when you think back here, in order to control the error and think of all the possibilities, we had this c written down here. So notice that this remainder, this error, is going to be less than or equal to the next derivative. So you should have already found through the 4th derivative, right? Yes? So the next derivative Now, what is this C all about? Remind me about that.
It has to be on the interval.
Yep.
We want it to make the function as large as possible.
Exactly right. So it should be on the interval, and we want it to make it as big as possible. Why do I want to make it as big as possible? Yes. Yes, so, and that sounds funny, doesn't it, to make the air as big as possible? So why do I want to make the air larger? Like, why would I make it bigger?
Because, like, with the skydiving being like the guarantee of the ground, it's easier than the guarantee that you won't be hurt.
Yeah, so it's like making a little bit broader target, right? You know, making a, Amber, your example was, I'll be there in an hour, right? Yeah, I might get there sooner, but I'm wanting to set it broad enough so that I can for sure meet it.
Yeah, I like to think of it as like throwing a basketball into a hoop versus into a swimming pool.
Which would you, if you're going to characterize a success, which one would you choose? Do you want the swimming pool? So, making it as large as possible. So we have this derivative. Now, if you notice, for this problem, I haven't really defined an interval. Okay? So what if my interval is from negative pi to pi? Okay? So that's the interval I want to define my air for right now, negative pi to pi. Now, I have some derivative, and I actually don't even have to necessarily look at it, because if I'm really just wanting to make this as big as possible, isn't it true that I'm at some derivative of a cosine, which means I'm either at a sine or a cosine? You know, this conversation would apply no matter if I'd say, wait a minute, I want the x to the sixth, I want the next term, like, isn't that derivative also some sine or cosine? And so if I think about on an interval, sines or cosines, what would the maximum for any derivative then that's sines or cosines from negative pi to pi be? 1 is the right answer. Why is that? Why'd she say 1? Why'd you say 1? I'll let you tell me. Yeah, so we actually, if you're just thinking sines and cosines, right, isn't there an amplitude of 1? So I'm at some derivative. Now, could we maybe do better? Well, if you look at this graph, and you could think about, okay, so I'm from negative pi to pi, I need to figure out what derivative I'm at, and so what is the fifth derivative of cosine? Negative sine. Now from negative pi to pi, will it take on a value of 1 or minus 1?
Yeah.
Will it? Anywhere on the interval, though. It doesn't have to be at the end. Will anywhere on the interval it take on the value of 1? Pi over 2, right? It's a sine, right? So there is going to be a moment where the sine curve, this derivative, is going to have the value of 1. So to compensate for that, or in order to hit our target, then this value here for our calculation then is going to be 1. So I'm also then going to take it and divide by, well, it's the next term. This is that factorial from creating that Taylor polynomial, right? So 5 factorial will go here. We've already said that a is 0 because you were centering this at 0, right? You didn't really ask. You just started. By the way, I don't know if I've said it, but if I say a Maclaurin, what I'm saying is it's a Taylor centered at 0. So if I say Maclaurin, I don't have to tell you where it's centered, by the way. So you might have seen that in the homework. So then I get this piece. Like, I know what n is, right? N is 5. It's that next term that we're not writing. So this was 5. This was that. I'm sorry, n is actually 4. So this is 5, 5. So what is x then? What are we also choosing for x? Going back to our example. So my interval, I didn't write it, was from minus pi to pi. So far we have a calculation that looks like this. So I'm saying that my error should be less than or equal to this. What is x though, Jackson?
I believe it's also a number on the interval that would make that separate calculation as big as possible.
Yeah, and again, so if we think about it, and we can see this graphically again, doesn't the polynomial start to deviate from the the cosine function here at the ends? Right? As soon as I'm moving farther away from where it's centered, that's where the largest deviation happens. So if you were looking at this and I'm saying I'm going to use that polynomial down here and I'm going to approximate the cosine function, you'd be most worried if I picked what x value to approximate it. Pi, or in fact, negative pi, either of those, they're going to be equally bad, by the way, because of the symmetry here. So again, if you're going to make a guarantee to me that that polynomial is good within a certain range, you would want to think about where it's the worst again. It's definitely going to be the worst at pi. So I'd go back to my calculation. X is pi. It's really the absolute value here, so if we would have said the negative pi, that would have been just as good, same result. So our answer looks like our error should be less than pi to the 5th over 5 factorial. And just do that real quick. What is pi to the 5th divided by 5 factorial? Use your calculator. I wasn't expecting you to do it in your head. Pi to the 5th is the hard part of that.
2.5. No, it's the easy part.
2 point what?
2.5.
So it's really r sub 4 because it's the error that's corresponding to that. Now, so what that means then is if I go back here again and I look at this, then this answer that we're getting for the polynomial here, so do you see that if I think about plugging in pi to the polynomial, it'd be about that y value. And graphically looking at that, you can see, what is it, maybe 0.2-ish, something in there. And if you look down here, I mean, I'm definitely within that target, aren't I? Now, again, the target might have been too large, so maybe we could have done better somehow, but we're just making a guarantee. I can guarantee your value won't be wrong by more than 2 point whatever that was. Okay?
But we're like answering questions like this, will there ever be will like we answer with a number, or do you want us to answer with like a sentence, like this first fast one's like answering.
Usually we'll do the calculation, and unless it's asking you to justify, we just are done at that point.
Is it always the case where your Taylor polynomial fits the best towards the middle or the center?
It's always going to fit the best at wherever it's centered, because that's the moment where you're actually constructing it. That's where all of those tangents, the derivatives, right? You keep evaluating the derivative where it's centered, and it's x minus a. So everything is always going to fit the best where it's centered. So here's practically then the thought: if that error is too much for us, what do we need? More terms. We need to just add some terms here to the Taylor polynomial. So now we could construct this error pretty simply. Still from negative pi to pi. I've added now through, so this is the 8th, x to the 8th. Couldn't you also right now just do a very simple calculation and guarantee my error is less than some value? What are you going to do? All I heard was, pi to the 9th over 9 factorial. What does that turn out to be? It is a number. Very good. You proud of you. Now what? Well, you're sarcastic, so.
0.082458.
Okay, so now we're saying that I can guarantee that the answer, if you choose any number from negative pi to pi, we're not going to be wrong by more than that 0.08. And now whatever you say, be sure you round up, right? You want more error, don't round that down. Okay. So if it's 0.08, what's the next digit? 2, 1. So you could say 0.0822. You'd want to say that you're within that range. Don't round that value down. Yeah, it'd be wrong. It'd be wrong. All right, so let's do something else here. So with all of that, let's look at a couple other examples, and then we'll... I want to do, I think it's example 3. It's not example 3. Sorry, lost it. Oh, there it is. So here's the problem. This is a AP question from a couple years ago. So you don't need the graph yet, so let's look at a couple of these parts and kind of do them together. So it says, let f of x equal sine of x squared plus the cosine of x. And then they're giving us the graph of its absolute value of its fifth derivative over here. Okay, I'm not going to worry about that yet. It says, write the first 4 non-zero terms of the Taylor series of the sine of x about x equals 0. And write the first 4 non-zero terms of the Taylor series for sine of x squared about x equals 0. Now, if you think about the first 4 terms of the sine of x, you should almost be able to just write those down. Because it also alternates, right? And the sine is the one that is the odd powers, right? If you recall, sine is actually the odd function even. So if that helps you remember that. The cosine is the even one, right? Symmetry about the y-axis, if that helps you keep it straight. Now, so here's a thought. Look up here. This one's easy. And this one is too. Do not start taking the derivative. The first derivative isn't going to give you too much trouble.
Second product.
So, better thought. Much better thought. If you can write the sine of x, you can also write the sine of x squared very simply. Substitution is the key. Do it. Do part A right now. Notice it doesn't say degree 4. Do you see that? It says the first 4 non-zero terms, which may take you further. In fact, it will. In fact, you're going to go through degree what? 7 here. Okay, so hopefully that's what you have for the sine of x. So from that, Jackson said substitution. So if I'm looking for now what the sine of x squared is, oh, by the way, do you notice that this is just bonus, okay? Not what I'm talking about right now, but just notice, do you see that's an equal sign? And it's only an equal sign because of the dot, dot, dot. Otherwise, if this is not written, we should be saying the sine of x is about this polynomial, right? It's approximating it. Yes?
So even if they say range the first four terms, you're able to add dots and then make it equal to
So I would think, like looking at this, if you even just wrote sine of x is about, and then did that, you'd be fine also. You just definitely don't want to say the sine of x equals and then not include this. That looks really bad.
I used to go like T7 equals and not
You could say that too, like something like that. Now, so if you're thinking substitution here, so this should have been your answer. Right? Basically, everywhere I see an x, I'm going to put an x squared, so that's what it is. Questions there?
How does that like work? If we use the curve, it's like non-polynomial stuff.
Yeah, so you're thinking about like, just like if it was the sine of 2 theta. So if you would actually need to say u equals x squared, and then think about, well, can you say that then? Because what's the derivative? We did look at that one in class, though. We turned that into the cosine of 2 theta to do it. So it gets worse and worse from there. So if you try to do it from that point of view, that's a bad idea. All right, so part A is all we've done. Part A is the part they expect you to get.
Are there parts they don't expect you to get?
Well, maybe. That's the part to boost your confidence. So here's part B,
Or wreck it.
or wreck it if you can't do the easy question. It says, now write the first four non-zero terms Taylor series for cosine of x about x equals 0. Well, we just wrote several of those. And then it says, use this
That's fun.
to write the first four non-zero terms for f. Remember, f is up here at the top. If my pen would work, I'd highlight it. So there's your f function. Do you notice that if I can write a Taylor polynomial for the sine of x squared, if I can represent that, and I can represent cosine of x, wouldn't I just add these polynomials together that I'm working with? So that don't make it harder than it is. We're just kind of building it. So if I can write a polynomial for the sine of x squared, what it would be equal to if I'm writing out the first four terms, so I'm saying about, then cosine of x would be about. So wouldn't I have something that would be about this function just by adding it? So take a minute to do that. Cosine should have been the easy part. Alternating and even powers. Sorry, yep. We're really just trying to write this now. The first four non-zero terms of this Taylor, of the Taylor series that corresponds to this, I should say. What's the first term of the for the Taylor for the function? Still 1. Next term.
X squared.
X squared over 2. Why is it over 2? Well, if you look at the sine of x squared, it's really x squared over 1, right? You substituted an x squared for an x. this is minus 1/2 x squared effectively. So plus 1x squared minus 1/2 x squared plus 1/2 x squared.
Did you have to simplify it like that to get the points?
You should be able to do that, yes.
Was the original function sine of x squared minus cosine x, or always plus?
Did you jot that down, Ron?
Yeah.
That'll mess you up.
Yeah. Well, yeah. Oh.
So here's the big thought. If you can do this, think about just adding the two equations together, right? Add yellow to blue. So on this side, we'd get sine of x squared plus cosine of x. That's what we want, right? And then on this side, well, it would just be, well, I have to add just like terms together. So that's where the 1 here comes from. There's your 1/2. So here I have the x to the 6th. Well, this one has an x to the 6th. This one doesn't have an x to the 4th, which is why this one just drops down. So this is minus 1/6 x to the 6th. Six factorial. 720. So if you're making a common denominator of 6 factorial, there you go. So just make it simpler. Just think of it as, if I would say minus 1/6 x to the 6th minus 1 over 6 factorial x to the 6th. This is the calculation that we're doing to get that result. Right? We're just combining the like terms together. So if you use your calculator and just say minus 1/6 minus 1 over 6 factorial, it's 121 over 6 factorial. So you just think, what do I need to multiply this by? Isn't it really this? So if I'm being clever, couldn't I just take this first fraction here and multiply by 5 factorial over 5 factorial? What is my denominator now? 6 factorial. So negative 120 minus 1 minus 121.
Why didn't they include the like extra 10 over 5?
So it did say, so here's an important point. Do you notice it said, again, write the first 4 non-zero terms? So I have now the first 4 non-zero terms. I can stop. So notice that they're not saying... So it's saying write the Taylor series for f. So I'm really wanting the polynomial that is f, not an approximation of f. So that's why ...
So would you, like, if you were taking the exam, would you want to include that?
Well, I think you'd get away with it here because it's really just saying write the first 4 terms. If we look at it, we can see what they've written here. So here's the scoring guideline of how they would award points for this. And so looking at it, and since they're wanting you to write the function, they may have marked that wrong if you hadn't included it. That would be tragic. They often don't give partial credit. It kind of is or not. So here's the good news. Here's the good news. You ready?
There's still 2 or 3 parts left.
There are more parts, except on these free response questions, they're 9 points each. They're always 9 points. So most of the problem you've actually already completed. So let's go back. So now let's look at something that's actually the Lagrange error. Well, C is easy. So decide what C is. What's that notation telling you to find?
So it's just the negative 1.
sixth derivative.
So it's the, yes, plug in 0 to the sixth derivative. So somehow that answer, it's for f. Did you notice that? Wait, for f, which f is this, that function that we're messing with. And if you're looking at what you just wrote down, we should be looking at this somehow. You okay with that? So tell your neighbor what the sixth derivative evaluated at 0 is. Talk. What is it?
All the yeah.
Your Taylor polynomial. Is this your Taylor polynomial? Factorial?
Factorial, yeah. And factorial. And so then like
What's the answer?
derivative is the part in front of the x.
What's the answer?
Negative 1.0.
It is not 0. It is not 1.
2?
1.1.
It is not 2. No.
Is it negative 121?
Megan's right.
Okay.
Megan, care to explain? Listen to Megan, please. Give it a try. I'll help. You're not listening. Hang on. Listen. Respect. Yep.
It's just a sixth derivative evaluated at 0, like the coefficient of function.
How come you ignored this, 6 factorial?
Because that's like the writing characteristics of what you do. It's not like part of the derivative.
Yes, exactly. So, in fact, when you're making that Taylor polynomial, isn't there always this like n factorial that you're doing down here, but you're evaluating it at the nth derivative, evaluated at whatever that x is, but then you divide by n factorial? So you just can look here and go, okay, it must have been minus 121. Okay. So, last question then. Let's see, that one was probably a point for the right answer. Last problem. So here we go. Now we need the graph. It says, let P sub 4 be the fourth degree Taylor polynomial for f about x equals 0. Using the information from the graph of y equals this fifth derivative, show that's true. Show that the absolute value of P4 evaluated at a quarter minus f of a quarter is less than 1/3000th.
Oh, wait, the graph
Talk about that.
Yeah.
Talk about that.
You plug in 1 and subtract. That's the derivative. No. Well, maybe you just like. Could you just do the Lagrange here the other way and then just the Lagrange here was less than 1? Let's do that.
All right, so let's take a piece of it. So if you look at the graph, notice that this is the next derivative, right? They're saying stop at the fourth one. And then they're saying, okay, so the next derivative, that's our air idea, right? It's wrapped up in the next derivative. So we were supposed to be figuring out on our interval. Now, so here, well, that's really all we have of it. But everything here is happening at a quarter, right? Interested in a quarter. So how does the graph help me? I'm just going to ask that. So Melissa, your question, is that the interval? Like, so let me say it this way. It's the only number I care about the error for. So I'm not really interested in the error. Notice that it's a single calculation I'm interested in, right? I'm interested in a single calculation and showing that the error there is no more than something. How about this? Maybe I should show you a piece of it. I know. I don't want you to see all of it. So look at this statement. There's more to it actually here. So I'm going to show you that there's more. Let's think about the pieces again. Come on, focus. They're saying the max of that derivative from 0 to a quarter. Why would I even be looking 0 to a quarter? Well, one thing, what's true about this graph? Okay, there's symmetry going on. And where's this thing centered? It's centered at 0. Think about the things we've already described, right? In fact, where's the most error occur if I'm trying to worry about a quarter, but I've centered it at 0? It's got to be a quarter, right? If that's the end of the interval, I can treat it that way right now because I don't care about any more. So look at the graph. That's the fifth derivative, right? That's the next derivative. And so here's 1. So actually every vertical line tick mark along that x-axis, how much is it representing? It's a quarter. And we want to hit the target.
Did you maximize it? With 40, just say around, be like, okay, it's now that much.
So what is this going to be, this piece that I'm almost showing you? It's going to be a quarter what? What's got to be there as well? It's got to be to the 5th. Are you okay with that?
Yeah.
That's where the most error is going to happen, on 0 to a quarter, at a quarter. And so look at this statement. I'm going to say it's less than that. Now, James, I think you actually said a second ago, call it 40. And so notice that there is a 40 in the problem here. And so it's saying 120, that's the 5 factorial. The 4 to the 5th, isn't that really all this is? 1 quarter to the 5th. So, James, why the 40?
Because you could call it 30, but you want to call it 40 just to be safe and absolutely prove it. Because if you round down, you might round it down too far, and you start getting into a lot of territory that you don't know what's going on.
So, where are you looking at the graph? How about that?
At the tick mark at under 40, but like it's a lot safer to estimate 40 than it is to estimate 30.
Yeah, so if you think about, okay, so this would be 20, so this, oops, this would be 30. 30 would be a little risky then. And even 39 or 38, like why don't you just say 40? It's clearly below 40. So from 0 to a quarter, this curve is definitely no ever bigger than 40. Now, we were supposed to prove this though, that the error is less than 1 over 3,000, right? So what's our calculation then? We had 40. So that's our max. Then we had our 5 factorial. My pen will cooperate. Which it won't, yes. And then we had our quarter to the 5th power. So what does that simplify to?
Is it something smaller than 1,000?
I hope so. I really want the fraction here, so if you can give me the fraction.
1 over 30,
30, 72, like that?
Yeah.
So that number is bigger, is it?
No, smaller because the denominator's
The
bigger.
denominator is larger. So did I prove it? Did I prove that the error is less than? So really, if we were going to make the guarantee, we'd feel really safe saying that the error is less than 1 over 3072. And they said, can you show, did I say that? Let me, wait, did I say that backwards? Oh, okay, I was worried I said it backwards for a second. So we could make this guarantee. So if I could make this guarantee, have I already made that guarantee?
Yes.
I have. Because I'm saying, okay, it's less than this. I can hit this target, but could I hit, so thinking about the size of those. So bigger, smaller. You with me? So we've made it. Let's do something else. Talk about something called truncation error. Truncation error. Think about when you truncate a number, you cut it off. Yeah, it's not a rounding, it's a cut off, chop off, throw away idea. So if I truncate the number 2.34, I could cut this off and throw it away. If I truncate 2.39, it's also 2.3. I cut that off and throw it away. So it's not a rounding. So if I look at this, that's a 9, sorry, P9 of x. I'm looking for the polynomial. That corresponds to 1 over 1 minus x. This is one to know. We saw this the other day, actually, when we were talking about what kind of series. Power series, specifically what kind of power series. This is actually geometric. What is this then as a polynomial? This is one to know. Also 1 plus x. I think we did both of them. Do you have it?
1 plus x plus x plus x all the way plus 1.
So again, right now, ... means I can say equal to, correct? They're the same thing. This is that infinite sum, right? The sum of the infinite geometric is the first term over 1 minus r. So the first term here is 1, so the sum would be 1 over 1 minus, what's the common ratio here? X. So do you see that pattern, right? You see that? So the truncation error then says this. If I write the 9th degree, so if I would actually have this go out, and I would say this, 1 over 1 minus x is about 1 plus x squared plus x cubed plus ... plus x to the 9th and stop. I want to know how bad this would be. Okay, so again, managing the error, how bad is this as an approximation? So I can find the truncation error. So if you think about it, the piece that I should have added should have been this, plus ... Right? If I would have included that blue portion, I could have switched to an equal sign. So your task right now, you could say this, the truncation error is that.
It's true.
It's true. But there's a much better way to write it. So thinking about this statement, can't I actually write the truncation error as a function? So I can call it whatever I want, but why don't you take 30 seconds at your table and write what's the truncation error?
Yeah, I know. I switched the number 1
It's just different series, right? Series.
What is it? Amber, what did you say? How'd she do? Good. Then you all did well. So again, it's just that infinite sum. So we're just calculating it. That's our truncation error. One last thought. Oops, sorry. I'm going to look at something talking about the error for an alternating series. Okay? The error for an that's a good title. Put that in your notes. The error for an alternating series. Alternating just means it's plus and then it's minus and then it's plus and then it's minus, etc., etc. Okay? So I want you to watch it. So I'm maybe going to zoom in a little bit more here. Okay? So here's the first value. And there's the next. So it's going over because it's think of the next term, right? So now x is 1. Think of the y as the next value of that sequence. So then it's going to go to 2, and then 3. And so right now you can actually see here, it's a very small negative, right? You can see that? So it's going to alternate. So now it's going to become a small positive. But here's an issue. If this is actually converging, what's happening about the distance from these points to the x-axis? It's got to be decreasing, okay? And then so as I keep alternating, like even the program here is given up at some point, it just starts saying 0. So let me go back here for a minute. So if I have gone to these first 2 terms, and I think about this idea of the error and how much I'm off by. So if I'd stop after adding together the first 2 terms, so I have a y value of 1, and this y value, which I think is -0.5. Yeah, it's -0.5. So think about adding those together. And I stop and I say, therefore, I approximated, I think this is actually cosine that I'm working with here. If you look at that, I'm pretty sure that that's cosine, the definition I have here. And therefore, I've approximated cosine, but maybe not that well. My question is, where is the error? Where is the most error if I was going to make a guarantee? So let's think about this idea of distance. Okay? So this next point is above, and it's more above than this point is below. And as I go to the right here, then you can see the terms are going to 0, which is that whole idea. So I claim the most error is wrapped up is this next term. The most error is the first term I'm not using. I want you to talk your table for 2 minutes as to why. And this is only true, only true, because it's alternating. Why would the most error be wrapped up by saying, so whatever this distance is here, so let me move it so I can use a number. I can guarantee I will not be off by more than 0.04166666. Why does that make sense if it alternates? Talk about that.
The 11th term is this long. We have like a center of the 11th term is not going to have a number farthest from the x-axis. After the 11th term, it's all converged. This all is so small, it doesn't matter as much.
Adding that, right? Taking that away, more of the way.
Why does alternating hold the key to that conversation? Here's what you can't say, is that the terms get smaller. That's not enough. It actually has to do with the alternating idea. Anyone want to argue that with me? As soon as you get this done, you're done. Yes?
Does it have something to do with, like, so if you have like a positive distance from the x-axis, and then you have the next negative, it kind of takes away from that?
So we're going to add on a negative.
Yes.
So, and or vice versa, right? I'd start with a negative and add on a smaller positive. So why does that idea mean the error is wrapped up all in that next term? I can guarantee it will not be worse than the next term. Say that again.
Like the most extra distance that you have.
I like that answer. It's the most extra distance. It's the larger distance that we're going to ever be away, right? I'm never going to be more than that distance away because I'm going to get smaller, and now I'm on the other side of the axis. So it's going to be converging down. That's really the easiest way to decide something that's alternating. So I think I have an example of that in thinking about its error, but I don't think I'll do that today. Okay? So you do have some homework that's talking about those, the alternating series, and asking for the error. It's as simple as finding the next term that you're not using. Yes, there actually is another take-home quiz on this section that I posted today. It's not due till Monday or Sunday. Okay. Mostly, I just didn't want you to do it tonight. You should go to bed before that. I'm pretty happy with my deadline. Do it on Saturday at midnight if you want. So, That's it. Have a good night. Work on this.